Hello everyone. So welcome to another session. So in this session, we are going to discuss some numerical examples used on root locus. Okay. Let me share my screen. Yeah. So a brief recap. Okay, about the constructing the root locus. Right. What's the first step? Root locus starts at open loop poles and ends at open loop zeros. So keep in mind, open loop poles may be finite or it may be infinite. Okay, it may be finite or it may be infinite. Similarly, open loop zeros can also be finite and or it may be at infinity when k tends to infinity. Okay, the root locus ends at open loop zeros. Then, how many branches does a root locus have? As many as the number of open loop poles, which is same as the number of closed loop poles. Why? Because keep in mind, root locus means how the closed loop poles move as gain k varies from 0 to infinity. Okay, so root locus starts from open loop poles. So then onwards it proceeds as k varies from 0 to infinity, right? So the number of open loop poles or the number of closed loop poles will give you the number of root locus branches. Then root locus is always symmetrical about the real axis. That is true. Okay, because always complex conjugate pairs occur in conjugate pairs. In pairs only it occur, right? So root locus will be always symmetrical about the real axis of the S-plane. Then to determine root locus on the real axis, what is to be done? We have to choose a test point. Okay, choose a test point, and if the total number of real poles and real zeros to the right side of the test point is odd, then this point lies on root locus. I have already explained that. Okay, so you consider test point. To the right side of the test point, there should be odd number of real poles and real zeros. If that is the case, then the test point lies on root locus. Otherwise, it is not a portion of root locus. Now, what next? Root locus approaches infinite. So once it is along the real axis, it is guided. But once the root locus starts leaving the real axis of the S-plane, then it should be guided by straight lines called asymptotes. Okay. How to find the number of asymptotes? It is given by P minus Z, where P is the number of finite poles and Z is the number of finite zeros. And all these asymptotes will meet the x-axis at a point called centroid. Okay. So whose axis are x coordinate is given by sigma p minus sigma z divided by p minus z. Okay. So all these asymptotes will meet the real axis. Okay, and we know that along x-axis y coordinate is 0, right? So this is the axis sigma p minus sigma z divided by p minus z. Okay, at some particular angle called angle of asymptotes given by this expression, plus or minus 180 into 2n plus 1 divided by p minus z. Okay. Then we have to find the breakaway or breaking points if there are any. Okay, so they can lie either on the real axis between two adjacent poles or zeros, which are on the root locus or always occur in complex conjugate pairs. Okay, so there may be a breakaway point on the real axis, or it can occur as a complex conjugate pair in the S-plane, as discussed in the example in the root locus video. Okay, so if the value of k corresponds to a root S1 of dk by equal to 0 is a positive real number, okay, then the point is a breakaway point. So how to check it numerically whether a given point S1 is a breakaway or not? What you have to do is you substitute that value into the you differentiate first. First you differentiate the equation in k. Okay, so we know what is Cap's equation: 1 plus k GSH is equal to 0. Okay, 1 plus k GSH is equal to 0. From here you separate out what is your k. That will be 1 by GSHS. Of course, minus of. Okay, so differentiate that with respect to S. So put dk by equal to 0, you will get candidate points. So how to determine whether those candidate points are actually breakaway or not? Substitute them back into this k equation. Okay, you will get into k equation. If k is a real positive number, then S1 is a breakaway point. Otherwise, S1 is not a breakaway point. Okay, then we need to find what is the angle of departure. So if you have a complex conjugate pole pair, we need to find what's the angle of departure. Okay, how to find that? Angle of departure from a complex pole is given by 180 degree minus sum of angles of vectors to the complex pole from all other poles plus sum of angles of vectors to the complex pole from all zeros. If it is an angle of arrival, if you have two adjacent zeros which are on root locus, then you will find what is angle of arrival. How to find that? 180 minus sum of angles of vectors to the complex 0 from all of the zeros plus sum of angles of vectors to the complex 0 from all other poles. Okay. And finally, you can find where the point at which root locus crosses the imaginary axis. How it can be found by putting s equal to j omega in the Cap's equation. Okay, by putting s equal to j omega in the Cap's equation, equating the real part and imaginary part to 0. Okay, by putting s equal to 0 in the Cap's equation, equating both the real part and the imaginary part to 0, and then you solve for omega and k. So when you equate real part and imaginary part to 0, you get two equations and two unknowns. One unknown is k and one unknown is omega. So two equations, two unknowns. They can be solved for finding the value at which root locus cuts the imaginary axis. Okay, let us take one problem now. GSHS equals k divided by s into s plus 2 into s plus 4. Okay, k divided by s into s plus 2 into s plus 4. Okay, so what's the first step? We need to find the points at which root locus originates. Okay, so one, root locus starts from open loop poles. Open loop poles. Okay, where are the open loop poles here? S is equal to 0, minus 2, and minus 4. Okay, and root locus ends at open loop zeros. Okay, here we do not have finite zeros, so it terminates at s is equal to infinity, infinity, infinity. Okay, then what was the next step? Root locus has as many branches as the number of open loop poles. So root locus has number of root locus branches. Number of root locus branches. Number of root locus branches. It's how much? Same as the number of open loop poles or same as number of closed loop poles. Okay, so it is 3. So there are 3 number of root locus branches. Now what next? Root locus always symmetrical about the real axis. Okay, root locus is always symmetrical. Always symmetrical about the real axis. Okay, now what next? We need to find root locus on the real axis. Okay, so root locus on the real axis. Root locus on the real axis. Okay, so let us consider a figure like sigma g omega. Okay, what is the open transfer function? K by s into s plus 2 into s plus 4. So that's one pole at 0, one at minus 2, and one at minus 4. Okay, so what to do? How to find the root locus on the real axis? We need to choose a test point. To the right side of the test point, there should be odd number of real poles and real zeros. Okay, so let me put my test point here. How many real poles and real zeros I have to the right side of that? 0, which is even. So that means in this interval, there is no root locus. Now we put the test point here. How many real poles and real zeros do I have to the right side of this test point? It is 1. So wherever I put my test point within this interval, always I have one real pole to the right side, which means this is a part of root locus. This is a part of root locus. So one will start from here, one will start from here. Okay, so I can wipe off this test point now. So I have determined root locus there. Now put the test point here. Now what happens? How many real poles and real zeros? 2, which is even. So that means between minus 2 and minus 4, there is no root locus. Then let me put a test point here. How many? 3 number of real poles and real zeros in total. Okay, to the right side of the test point. So that means from minus 4 to minus infinity, we have another root locus branch. Okay. So that means this goes to minus infinity. Okay. Goes to minus infinity. So we have determined the root locus on the real axis. Right. What next? Now we have to determine asymptote. So you see here, the root locus is coming. So there is a breakaway point at which they will merge. Okay, they will hit and then they will split apart. So there is a breakaway point here. Why? Because we have two adjacent poles which are a part of root locus. Okay, so next one is breakaway point. Sorry, now number of asymptotes. Okay, asymptotes, right? So number of asymptotes. Number of asymptotes. So how to find number of asymptotes? That is given by P minus Z. Okay, number of asymptotes is given by distinct asymptotes is given by P minus Z. Okay, where P is the number of finite poles and Z is the number of finite zeros. Okay, so and here we have 3 finite poles and 0 finite zero. So that means P minus Z is 3. P minus Z, which is 3 minus 0, which is equal to 3. So these asymptotes will meet the real axis at a point, okay, called centroid, whose abscissa is found. How can we find the abscissa? Whose abscissa is found given by sigma p minus sigma z divided by p minus z. Okay, so we have to add this thing, centroid. Centroid abscissa, okay, because on the x-axis, y quantity is 0. So we need to find the centroid abscissa, okay. That is given by sigma p minus sigma z divided by p minus z. Okay, what is sigma p? You add 0, minus 2, minus 4. Okay, so minus 6. Minus 6 divided by 3. That means minus 2. Okay, now what next? Angle of asymptotes. Angle of asymptotes. How to find that? Plus or minus 180 into 2n plus 1 divided by p minus 7. Okay, where n varies from 0, 1, 2, etc. Okay, so we have 3 asymptotes here. So we need to find 3 asymptotic angles. So first you put n equal to 0. What will you get? Plus or minus 180 by 3. Okay, because p minus z, number of finite poles minus number of finite zeros is 3 here. So you will get plus or minus 60 degree. So 2 angles we got. Then we have a third asymptote as well. Right? So how to find the third angle of asymptote? You put n equal to 1 here. Take the positive value. So 3 and 3. So this becomes 3. 3 and 3 gets cancelled. It becomes plus 180 degree. Okay, so we had 3 asymptotes. We have found 3 asymptotic angles. Okay, what next? Now we need to find the breakaway and breaking points. Okay, so you see here the root locus starting from 0 at origin from origin and the one starting from minus 2. What happens? As k varies, they will move simultaneously and they will hit at a point. That point is called breakaway point. Okay, so next is breakaway point. How to find the breakaway point? Breakaway point. Okay, what's the Cap's equation? 1 plus a by s plus this thing equal to 0, right? 1 plus GSHS equal to 0 is the Cap's equation. Okay, so if you do that, you will get from here s into s plus 2 and s plus 4 plus k equal to 0. Okay, s into s plus 2 into s plus 4 plus k equal to 0 is the Cap's equation. 1 plus GSHS equal to 0. So what is k from this? K is minus s into s plus 2 into s plus 4 into s plus 4, right? That much, right? So that turns out to be minus s cube minus 6s square minus 8s. Now what we have to do? Differentiate that. dk by ds equal to 0. What did you get? Minus 3s square minus 12s minus 8 equal to 0, right? So if you solve from this, you will get your candidate points as s is equal to minus 0.845. Okay, you will get this as minus 0.845. Minus 0.845. So if we solve this, it is a quadratic equation. You will get two values actually. Okay, so s1 is s equal to minus 0.845 and another one is minus 3.1547. Out of this, which could be a breakaway point? Please look here. We have root locus between 0 and minus 2. So naturally, the natural choice is this thing, minus 0.845. Okay, or mathematically, you can check that value. How? You substitute this thing. Okay, say into this k equation. You substitute this, find what is the value of k when s is equal to minus 0.845. Okay, that means you substitute it here. So minus of s into, so s is minus 0.845 into minus 0.845 plus 2 into minus 0.845 plus 4. Okay, If this number is a real positive number, then this is a breakaway point. So we solve this and you will see that it will be a real positive constant number. Okay, so that means minus 0.845 is a breakaway point and minus 3.1547 is not a breakaway point. Okay, so this is not a breakaway point. You can substitute this value into K equation. See that this will not be a real positive number. Okay. So we have found our breakaway points. Right. Now what next? So you see this our centroid is at -2. Okay, this is our centroid. Yeah, and we have three asymptotes. Now let me mark this. Okay, so centroid is -2. Say this is +60, this is -60, and then we have 180. So 180 already it is there. Okay, already the third branch of root locus is on the 180 degree axis. Okay, so this is +60, -60. Okay, so now we are definite that root locus will be crossing the j omega axis, the imaginary axis. What is the significance of imaginary axis? It is a stability boundary. Okay, it's a stability margin, stability boundary is that j omega axis. So now we need to see at what frequency and at what gain k the root locus will cut the imaginary axis. Okay, that is the next step. How to do that? We had already seen that we have to substitute s is equal to j omega in the Kapp's equation. Okay, s is equal to j omega in the Kapp's equation. Right? So here we do not have any complex poles. So we can ignore this seventh step. Angle of departure will not be applicable here. Right? So now we need to find what is how at what point the root locus will cut the j omega axis. Okay. So how to find that? Putting s equal to j omega and equating real part and imaginary part to 0. Fine. Yeah. So what was the Kapp's equation? Kapp's equation was 7. So now we need to find the j omega axis crossing. Okay. What is our Kapp's equation? This is our Kapp's equation. S into s plus 2 into s plus 4 plus k equal to 0. Substitute s is equal to j omega. Put s equal to j omega. So what will you get? J omega into j omega plus 2 into j omega plus 4 plus k equal to 0. Okay. So if you expand this thing, you will get minus j omega cube minus 6 omega square plus j 8 omega plus k equal to 0. Now we equate the real part to 0, imaginary part to 0. So you will get 6 omega square j omega cube. Okay. So you will get k minus 6 omega square equal to 0 and omega cube minus 8 omega equal to 0. So that means from here you will get omega square as 8 or omega will be root 8 radians per second. Okay, so substitute that into this equation. So from here you will get k equal to 6 into 8, which is 48. Okay, so how will be the root locus? It will be something like this. This is sigma j omega plane. Okay, we had a pole at 0, -2, and 1 was at -4. Okay, so what happens? This is a part of root locus. We had already seen that. And it goes to -infinity. So our centroid was at -2. We had two asymptotes, plus 60, -60. Okay, so one root locus originated from here, another one originated from here. Right? Where was our breakaway point? Our breakaway point was at minus 0.845. That means somewhere here. Minus 0.845. Okay. So from now we have also found what frequency cuts the j omega as √8. Say maybe let this be j √8. This be say minus j √8. Okay. So your root loss will be something like this. Starts from here. And then onwards a freehand sketch along the asymptote. Along the asymptotes, just do a freehand sketch. Okay. So this will complete the root locus for this problem. Okay. Let us try another one. GSHS equals K divided by S plus 1 into S plus 2 minus J into S plus 2 plus J. Keep in mind, we are considering the cases where K is greater than 0. Okay, that's very important to know. If K is less than 0, all the rules will not be applicable in the same manner. There will be slight modification. Okay, we are considering only positive gain values. Okay. Again, as before, what's the first step? We need to find the starting point. Okay, so root locus starts at open loop holes. Root locus starts at open loop holes. Where are they? S is equal to -1, -2 plus minus T. Okay, and root locus ends at open loop zeros. Where are they? Infinity, infinity, infinity. Okay, what's the next point? Number of root locus. Number of root loci. How much is that? Same as number of open loop holes. That means 3. Okay, then root loci is always symmetrical about the real axis. Root locus is always symmetrical. About the real axis. Okay, what next? We need to find root locus on the real axis. Root locus on real axis. Okay, so for that you consider the S-plane with open loop holes. One was at -1, and then we had one at -2 plus minus G. So this is -2, this is plus J, and this is minus G. Okay, how to determine root locus? Consider test point. To the right side, there should be odd number of real poles and real zeros. Okay, so if you put the test point here, you will see that from -1 to -infinity, wherever I keep my test point, it is always odd. That means there is a root locus branch starting and going like this, -infinity. Okay, there's a root locus branch like this. One branch is going like this, right? That part we did. Now what next? Next is asymptotes. Okay. Now, how to find asymptotes? Number of asymptotes. That is given by P minus N. Okay, where P is the number of finite poles and this is the number of finite zeros. So here we have 3 finite poles and no finite zeros. So that means P minus that is 3 minus 0, which is 3. Okay, next we need to calculate what is centroid, axis of the centroid. Okay, how to find that? Sigma P minus sigma Z divided by P minus Z. What is sigma P? You add these things. -1, -2 plus J, -2 minus J. That means -4. Okay, so -4, then sorry, this is plus. Oh, sorry, -1 plus -1, -2 plus J, -1, -2 minus J. That means -5. Okay, so you'll get -5 divided by 3. That turns out to be -1.66. Okay, what next? Angle of asymptotes. Angle of asymptotes. How to find that? Plus or minus 180 into 2n plus 1 divided by P minus N, where n varies from 0, 1, etc. Okay, so you put n equal to 0. P minus N is 3 here. Okay, so you put n equal to 0, you will get plus minus 160. Sorry, plus minus 60 degree. And you put n equal to 1. So you will get 180 degree. So as you can see here, already it is on 180 degree line. One of the branches is on 180 degree line. So now we need to construct 2 more asymptotes. Okay, one at plus 60, one at minus 60, like this. Okay, what next? Then here we have there is no breakaway point. Okay, there are no 2 adjacent poles which are a part of root locus. So you can skip that and jump to the next. Okay, now we have a pair of complex conjugate poles. That means we need to calculate what is the angle of departure. How to do that? For that, you join this particular angle complex pole with all other poles and zeros. Okay, so this is 1, this is 1. measure the angle. Okay, this angle, let it be theta 2 and let this be theta 1. Okay, what is theta 2? Plus 90. It's evident. And what is theta 1? Theta 1 will be this much is 90 degree. Okay, so 90 plus tan inverse what? Opposite side by adjacent side. Opposite side means 1 divided by 1. Tan inverse 1. That means 90 plus 45, which means 135 degree. Okay, so what is the next step? Angle of departure. Angle of departure from minus 2 plus g will be equal to 180 minus sum of angles from pole. That means 90 plus 135. And that turns out to be minus 45 degree. Okay, minus 45 degree. Now what next? Since these asymptotes are at an angle, they will cut the j omega axis. So as a next step, we need to calculate what are the j omega axis crossings. Okay, next step is j omega axis crossings. How to find that? Put s is equal to j omega in the Cap's equation and solve. Two equations, two unknowns. Okay. So what is our Cap's equation? S plus 1 into this thing plus k equal to 0. Okay. So our Cap's equation is s plus 1 into s plus 2 plus j into s plus 2 minus g equal to 0. So you put s equal to j omega, you will get j omega plus 1 into j omega plus 2 plus j into j omega plus 2 minus j equal to 0. So do a simplification, solve this, you will get k plus 5 minus 5 omega square plus j 9 omega minus omega cube equal to 0. Now what is to be done? Equate the real part to 0, imaginary part to 0. So you will get k equal to 5 omega square minus 5 and 9 omega minus omega cube equal to 0, or 9 omega equal to omega cube, or that means omega square equal to 9 or omega equal to 3 plus or minus 3 radians per second. Okay, so since omega equal to 3, you can find what is k. You just you have to substitute into omega square. So this is 45, omega square is 9, 95 is 45, 45 minus 5 is 40. Okay, so it will cut this at j3. This is plus j3 and this is minus j3. Okay, so you can measure what is 45 degree from here. Maybe use your protractor. So this is, you just draw it. Beautifully you draw. It should cut at this point. Okay, you might ask at that. Okay, let me draw it here once again. Right? If you can draw it on a graph sheet, it will be better. This is sigma j omega. We had a pole at where? Pole at minus 1 and 1 at, this is minus 2 plus j, and this is minus 2 minus j. Okay, so this was one root locus. Okay, and then we drew asymptotes. Where was the asymptotic point? It was at centroid, was at minus 1.666. So maybe centroid is somewhere here, minus 1.666. So this is at plus 160, sorry, plus 60 minus 60 in the line. Okay, so if this is plus j minus j, maybe somewhere you take the scale appropriately. Okay, so this will be, you can measure how much is 45 degree minus 45 degree. That will move like this. It will move like this. Okay, and here also it will move like this. It should be symmetrical. Okay, but symmetrically you can draw. So this way you can find what is the root locus. Okay, let's take another example. Let's take another example. GSHS equals K divided by, next example, GSHS equals K divided by S square plus 10S plus 100. Okay. So where are the close two poles? You factor this thing, you will get S plus 5 plus J 8.6602 into S plus 5 minus J 8.6602. Okay. So root locus starts at open loop poles. Root locus starts at open loop poles. Okay. Where are the open loop poles? S is equal to minus 5 plus minus J 8.6602. And root locus ends at open loop zeros. Ends at open loop zeros. Where are they? Infinity, infinity. Okay. Now what next? Number of root loci. Number of root loci. How many? 2, because we have 2 open loop poles or 2 closed loop poles. Okay, so there will be 2 number of root locus branches. Then what next? Root locus is always symmetric about the real axis we explained. Root locus is symmetric about the real axis of explained. Okay, what next? So we see where if you draw root locus on the real axis, root locus on real axis. Okay, sigma g omega. Where are the poles? It is minus 5. So this is minus 5 plus J 8.6602. This is minus J 8.6602. So here root locus on real axis does not exist. Why? Because we do not have any real pole. Okay, so you can jump to the next step, right? So root locus on real axis step is not valid here. Okay, so going to the next step, what will you get? Next step, we have to find number of asymptotes. Number of asymptotes. How to find number of asymptotes? P minus F. Okay, where P is the number of finite poles and Z is the number of finite zeros. So here we have 2 finite poles, right? So it will be P minus F is 2 minus 0, which is 3. Now what next? Centroid, abscissa. Sigma P minus sigma Z divided by P minus Z. So sigma P, what will you get? Minus 10. Okay, sigma Z, we do not have finite 0. So sigma Z is 0. Okay, so minus 10 divided by 2. That means minus 5. Okay, so here it so happens that our centroid is at minus 5. Right? Now, next is angle of asymptotes. Angle of asymptotes. Angle of asymptotes. How to find that? Plus minus 180 into 2n plus 1 divided by P minus F. Okay, put n equal to 0, 1, 2, etc. Right? So you put n equal to 0. P minus Z is 2. That means you will get plus minus 90 degree. Okay? So centroid is minus 5. So this is our asymptote. One is at plus 90, one is at minus 90. Okay, these are the asymptotic lengths. Right? Now what next? We need to calculate. So since we have a pair of complex conjugate poles, we need to determine what's the angle of departure. Okay, so how to find the angle of departure? How to find the angle of departure? Next step is angle of departure. Angle of departure. 180 minus sum of angles from other poles. Okay, so here you have only one pole here, right? So what is this angle? It is plus 90. So 180 minus 90 degree. That means 90 degree. Okay, angle of departure from minus 5 plus J 8.6602 from minus 5 plus J 8.6602. So what will be the angle from minus 5 minus J 8.6602? It has to be minus 90. Then only it will be symmetrical about the real axis, about sigma axis. Okay. So if from here you are getting plus 90, this has to be minus. Correct? So what will be the root locus plot? It will be something like this. So one will go like this, one will go like this. Okay, this will be the root locus plot. If you do in MATLAB, you will get the exact shape. Okay, you can try drawing it on a graph sheet, on a linear graph sheet. You can try drawing this. Okay. Let us take another example. GSHS equals K into S plus 1 divided by S square into S plus 2. Okay. GSHS equals K into S plus 1 divided by S square into S plus 2. Right. So step 1, root locus starts at open loop poles. Open loop poles. Which are they? 0, 0, minus 2. Root locus ends at open loop zeros. Which are they? Minus 1, infinity, infinity. Okay. Because we have only one finite zero. Since there are three finite poles, there should be 3 zeros as well. Okay. And in which, out of which we have one finite zero and the remaining 2 are at infinity. Okay. Then what next? Number of root locus. How much? The same as number of open loop poles. That means 3. Okay. Then next step. Root locus is symmetric about the real axis. Root locus is symmetric about the real axis. Okay. What next? We have determined root locus on the real axis. Okay. So let me draw this figure here. Sigma g omega. Okay. Sigma g omega. So where are the open loop poles? There are 2 poles on the origin. Okay, at the origin. And then we have one at minus 2 and 1, 0 at minus 1. 1, 0 at minus 1. Okay. So how will you find root locus on the real axis? For that, we need to choose a test point. Okay. Put a test point here. How many number of poles are real poles and real zeros? Do we have the right side of this test point? Yes, tell me. How many number of real poles and real zeros lie to the right side of this test point? 1 or 2. Keep in mind, here we have a repeated pair of poles at the origin. Okay, S equal to 0, S equal to 0. One is sitting on top of the other. Right? So how many poles are there on the right side? It is 2, which is even. So that means this is not a part of root locus. Shift the breakaway point to this interval. So this will be a breakaway point because to the right side of this test point there is one pole at minus 1 and 2 poles at S equal to 0. So that there are total 3 number of poles. So that means within this interval there we have a root locus. Okay. So this interval there's a root locus. Right? The root locus starts from open loop pole and ends at open loop 0. Okay. So this will be the root locus on the real axis for this particular problem. Okay. Now what next? We need to calculate asymptotes. Yeah. Number of asymptotes. Number of asymptotes. How to find that? How to find that? P minus Z. What is P? Number of finite poles. That means 3. Z, number of finite zeros. That is 1. So number of asymptotes is 3 minus 1, which is 2. Okay. Which is 2. Number of asymptotes is P minus Z. Right. This is 3 and we have one finite 0 here. So 3 minus 1 is 2. Right. Then centroid. How to find centroid? Sigma P minus sigma Z divided by P minus Z. You add all the finite poles and add all the finite zeros, subtract it from the sum of finite poles. That's it. So you will get minus 2 minus 1 divided by 2. That means 0.5 minus 0.5. Okay. Minus 2 minus 1. That means minus 1 by 2. That means minus 0.5. Okay. So centroid happens to be at minus 0.5. Minus 0.5. Right. Now what next? We need to calculate angle of asymptotes. Angle of asymptotes. How to find that? Plus or minus 180 into 2n plus 1 divided by P minus. Okay. Where n varies from 0, 1, 2, etc. So put n equal to 0. What will you get? 180 divided by 2. That means plus or minus 90. Plus or minus 90. Okay. So This will be our asymptote. Asymptote will be like this. Okay. Now what happens? So what is the meaning? So now the remaining steps are not valid here because we do not have a complex pole. So there is no angle of departure. And it is not going to cross the imaginary axis. Why? Because the angle of asymptotes is plus or minus 90 degree. Okay. So all the steps can be ignored. So this has completed that construction rules. So how will the root locus move now? So from here, one will move like this along this asymptote and another one will move like this. Okay. Infinity, infinity. Okay. So this will be the root locus plot for this particular problem. Right? Let us try another example. Q. GSHS equals K into S plus 6 whole divided by S into S plus 4. Okay. This is a question. Show that root locus plot with K as variable parameter is a part of circle. Part A. Okay. Part B. Determine break away or break in points if any. Part C. Determine the range of K. For which the system is underdamped. And the value of K for critical damping. Okay. So how to start this? Again, as before, step 1, root locus starts at open loop poles. Where are the open loop poles? One is at 0, one is at -4. Right? And root locus ends at open loop zeros. Where are they? -6 and -infinity. Fine. Then root locus symmetry about the real axis. Number of root loci. Number of root loci is given by number of open loop poles, which is 2. Third step, root locus symmetrical about the real axis. Okay. So here, if you let us draw this thing, huh? Let us try to determine root locus on the real axis now. Root locus on real axis. Sigma j omega. Okay. What is the transfer function? S plus 6 by S into S plus 4. So there is one pole at 0, one at maybe this is -4, and 1 0 at -6. 1 0 at -6. Okay. Now, how do you determine the root locus on the real axis? Take a test point. So if you, wherever I put the test point in this interval, it is a part of root locus. So one will start from here, another one will start from there. Okay. One will start from here, another one will start from here. Right? So there is a breakaway point. Fine. What about the interval between -4 and -6? Is that on root locus? No, because wherever I put the test point to the right side, total number of real poles and real zeros is even 2. Okay, so this is not a part of root locus. Put a test point here. What happens? It is odd. So that means from -6 to -infinity, it is a part of root locus. Okay, from -6 to -infinity, it is a part of root locus. like this. Okay, so keep in mind, from pole root locus starts, and at open loop pole root locus ends. So this is one branch will end like this. Okay, another branch will go to minus infinity. Okay, so you can see that since there is a breakaway point in between 0 and -4. Likewise, there is a breaking point between -6 and minus infinity. Because you see, where are the open loop zeros? They are at -6 and minus infinity. So breakaway points occur between two adjacent poles and if they are a part of root locus. Similarly, breaking points occur only when you have two adjacent zeros and if they are a part of root locus. So we have two adjacent zeros, -6, minus infinity, and they are a part of root locus. So that means there will be a breaking point here. Okay, so that's a breakaway point and that's a breaking point. Let us find that. Breakaway point. Breakaway or breaking point. Okay, so what is k from this? K will be minus s into s plus 4 by s plus 6. How did I get that? 1 plus GSHS. Or I can write 1 plus k GSHS equal to 0. Okay, so 1 plus this equal to 0. So from this you separate out k. So k will be equal to minus s into s plus 4 divided by s into s plus 6. Minus s into s plus 4 divided by s plus 6. Okay, so this becomes minus s square minus 4s divided by s plus 6. Okay, so differentiate that. dk by dt is equal to 0. What would you get? You would get s as minus 9.464 and minus 2.536. These are the two values. Okay, so where is minus 2.536? It is in this interval. So that will be a breakaway point. If you have any doubt, you substitute this minus 2.536 value into this k equation and check if k is a real positive number. If it is, then minus 2.536 is a breakaway point. Similarly, how to find this, whether this is another breakaway or breaking point? Substitute this minus 9.464 into k equation. Check if k is greater than 0. It's a real positive number. If it is, then this is also another breakaway breaking point. So you can see that minus 2.5 is somewhere here. And minus 9.4 must be somewhere here. Okay, so this is a breakaway point, and since this is in between, lying in between two adjacent zeros, which are a part of root locus, minus 9.4 is a breaking point. Okay, so what happens? They will at the breakaway point they will come hit together. At the breaking point they will join and then. Okay, so we'll see that from experience we can draw. Okay, one branch will be which is circular. Okay, like this. Another one will be like this. One will start from here. So they will merge at this point, and one will go to the pole at -0 at -6, and one will go to the 0 at infinity. Okay, so this will be a part of circle, right? That can be proved actually. So what is the transfer function? K into s plus 6 by s into s plus 4, right? So what is the angle? Angle GSHS will be what? How will you find the net angle? Angle of s plus 6 minus angle of s minus angle of s plus 4. Is it not? A angle alpha into B angle beta divided by C angle gamma. What's the resultant complex number? AB by C. Angle alpha plus beta minus gamma. Same thing. Okay. So angle of s plus 6 is in the numerator, right? So angle of s plus 6 divided by minus angle of the terms in the denominator. So angle of s plus 6 minus angle of s plus 6 minus angle of s minus angle of s plus 4. Okay, so but we know, see, what is s? S is a complex number. S means sigma plus j omega. Okay, so we substitute that here. That means angle of sigma plus j omega plus 6 minus angle of sigma plus j omega minus angle of sigma plus j omega plus 4. Okay, how will you find the net angle? So what should be this total angle? This total angle has to be equal to 180 degree. Is it not? Because that's why it is called a root locus, right? So the net angle at those close to point has to be plus or minus 180 degree or odd multiple of that. Okay, so this will be equal to plus or minus 180 degree. Let me take it to be 180 degree. Okay, now how will you find the angle? This I can write tan inverse tan inverse omega by sigma plus 6 minus tan inverse omega by sigma minus tan inverse omega by sigma plus 4 equal to 180 degree. Okay, so let me take this term to the right side. So you will get tan inverse omega by sigma plus 6 minus tan inverse omega by sigma equal to 180 plus tan inverse omega by sigma plus 4. Take tangent on both sides. What is tan A plus B? Tan A plus B is tan A plus tan B. What? Tan A plus tan B by 1 minus tan A tan B. Okay, so if you take tangent on both sides, so this is A, this is B. So tan of A plus B, you will get omega by sigma plus 6 minus omega by sigma whole divided by 1 plus omega square by sigma into sigma plus 6 on the left hand side. Must be equal to what? Tan 180. That is 0. So 0 plus omega by sigma plus 4 whole divided by 1 minus tan tan, which is 0. Okay. So if you solve this thing further, you will get. If you solve this thing further, you will get minus 6 sigma minus 24 equal to sigma square plus 6 sigma plus omega square. Right? You simplify this further, you will get sigma square plus 12 sigma plus omega square plus 24 equal to 0. Right? So how can you complete the square here? You see, this you have sigma square, you have 12 sigma here. Okay. So a plus b whole square, a square plus 2ab plus b square. Okay. So a is equal to sigma. So 2 into ab, sigma into b must be equal to what? 12 sigma. So 2 will cancel. So this you will get 6. Sigma will get cancelled. So b is 6. So that means I can add and subtract 36. Okay, I can add and subtract 36 to this. So sigma square plus 12 sigma plus 36 or 6 square. Okay. So remaining terms I will take to the other side. So I will get this as what? Sorry, plus omega square. Okay. So you have to add and subtract 36. So you will get to 12 here. Okay, because 36 plus 36 minus 36. So 24 minus 36, it will be minus 12. Minus 12, if you take it to right hand side, it becomes 12. So what is this? This is nothing but sigma plus 6 whole square plus omega square equal to root 12 square I can write. Right? And what is this? This is the similar to equation of a circle. X plus a whole square plus y plus b whole square equal to r square. Where minus a and minus b are the circle center and r is the radius. So here, what does it mean? This represents a circle with center minus 6 comma 0 and radius root 12. Root 12. Okay, so we have proved that this will be a part of root locus. Now, what's the next part? We need to find what is the value of gain k for range of k for which system is underdamped. Okay, so see here, when will the system be underdamped? System will be underdamped when the poles are complex conjugate. Okay, that means it has to leave from this point, right? So this k value at this point, what happens? K, there's a particular value of k at which system is critically damped. And again, at this point, again, system becomes critically damped because critically damped means what? Those two poles are real and equal. Okay, and afterwards they are not real and equal. So between k value comes, say, let me mark this as k min and k max. Okay, so between k min and k max, the closed system will be underdamped. So how can you find that? You have to find what is the value of k at this particular point. Okay, so we know that this breakaway point is at minus 2.5, right? So that means you have to find the magnitude. K will be equal to what? 1 by mode GSHS at S is equal to minus 2.5. That will give you the minimum value of K for underdamped. Okay, that means if you substitute this into this thing and find the magnitude, you will get 1.07. Similarly, here it is minus what is that? Minus 9.4. Minus 9.4. 9.4. Okay. So what is the maximum value? So K max will be 1 divided by mod GSHs at S is equal to minus 9.4. And that turns out to be 14.928. Okay. So long as your gain K lies between 1.07 to 14.9282, system is underdamped. Okay, underdamped. And what is the value of K at which system is quickly damped? Obvious. When K is equal to 1.07 and when K is equal to 14.928. Okay, system will be quickly damped. Okay, so this is how to plot the root locus and get the salient points out of root locus. I hope it is clear to all. So we'll stop here. Thank you.